formal as you guys want and go in various directions. I do have a plan though. But feel free to ask questions. Okay. Last time I ended saying some quick things about Koszul duality. I just want to remind you of that and the simplest example, which I didn't give last time. And I am giving it now because I'm going to say the words Koszul duality a bunch later in the talk. And I think the example that I gave you last time was that modules developing algebra and modules, so this in both DG for Chevalier-Eilenberg. And thought it was a DG algebra, where equivalent is DG categories. But there's a much simpler example, which if you've never seen this before, is the first thing you should have in mind and maybe work out for yourselves. And if you have seen this, sorry to bore you for a few minutes. If we let our two-dimensional topological field theory just be a topological boson, scalar boson. X is the equation of motion is equal to 0. In order to impose this equation of motion, it ends up needing to be accompanied by a fermion. I don't want to go into now exactly why that's forced on you. And there's flexibility in assigning homological degrees. Nice choice that makes categories work out well. Is to give the boson degree 1. And then the action in multiforms. Just looks like that. It looks weird to pair a boson and a fermion in the kinetic term. What's actually happening is that so this is an dimensions, that's an integral over R2. It's picking out the two-form part of this, so it's pairing the one form psi, which is bosonic, with the zero form part of X, and stuff. So it's actually okay. This has transverse and complete boundary conditions. Which I like to call Dirichlet and Neumann, but that's from the perspective of the boson. From the perspective of the fermion, they're the opposite. So Dirichlet says the boson, but then you need, in order to make it compatible with BRST symmetry, you set the entire multiform restricted to the boundary to 0. Neumann sets the fermion and its accompanying multiform to 0. And then the algebra of operators on Dirichlet, since the boson has been set to 0, there's just being polynomials in the fermion, the algebra of operators on none, since the fermion is set to 0. Ends up being polynomials in the boson. And if the theory were any more complicated and had interactions, these wouldn't just be trivial graded commutative algebras. There would be differential and non-trivial commutators and maybe higher operations, but it's a free theory. So nothing like that can happen. Transversality, you can think of heuristically as the fact that if you squash the sandwich, everything dies. Psi dies on one side, x dies on the other side. Field theory is gone. But if you want to break that down a little more microscopically, transversality amounts in terms of algebras to saying that on a strip, if you ignore the other half of the strip, on each side there's this algebra of operators. But when you squash, there is an interaction through the bulk induced by the bulk propagator, which connects psi's and x's. And there are little Feynman diagrams that connect operators on the two sides and induce on a strip. So I sort of want to say this is on a squeezed together strip, the actual algebra in the end, like yes, AD sits on one side and AN sits on the other side, but the entire thing gets deformed by bulk interactions, which the only way they can possibly appear in something that's effectively one-dimensional is through a more Cartan element that deforms the differential. And the more Cartan element coming from this propagator is x psi. It has all the right degrees. And the cohomology of polynomials in x and psi with that differential multiplication by that is true. That's sort of like the very hands-on microscopic way to explain what transversality is. Anyway, so they both of these algebras act, but they act sort of from the left and the right on this bimodule, which is trivial. And then you get the standard Koszul statements that the category modules for each of them is SBG modules is equivalent. And to make sense of this, in fact, for the other example as well, just to say you need to be a little careful about what sort of modules you take. One way to do that is to take finite dimensional modules on the fermion side and finite rank. On the boson side, there are other choices. Okay. Working through this is, if you have never seen it before, is a really nice exercise. Yeah.
I have a very wishful thought question. Is this somehow related to bosonization?
Yeah. It absolutely is.
Let me rephrase. It's just a statement of the duality between boson and fermion.
Yeah. So it sounds like in bosonization, you're actually rewriting the fields of the theory, and that's not what's happening here. But like suitably massaged, one can understand bosonization as this sort of thing as well. Right? It's a vague answer, but yeah. Cool. Okay, so I'm going to switch gears entirely and move on to like what I had planned for lecture 2 or 3. I want to talk about sensor structures. So given a functor from a category defect with some endomorphism algebra and a lift, what happens if C is monoidal? And the answer depends strongly on how the putative fiber functor, how the functor defect interacts with the tensor product. And so you need to look at what the difference is between tensoring before and tensoring after. And I'm sorry if this is also totally trivial for some part of you. Then like that part can now. Different relations between tensoring before and tensoring after imply different ways in which the monoidal structure might be encoded in this algebra A. Specifically, the thing you would really like is to put some structures on A so that F tilde actually preserves the tensor product. And there are many options. And it really depends how these things differ or not. What should I say? Like the nicest thing you might want is like a coproduct on A and a bialgebra structure coming from a counit, maybe an antipode that knows something about duals in the category. That's more than the tensor structure. And so on. And then similarly, if the category is braided, maybe want to find a way to reproduce the braiding on the right-hand side of this as well with something like an R matrix.
Sorry, Tudor. So maybe before this bialgebra story, so you're wanting to compare F, tensor, F and then tensor, and tensor and then F, But is there a well-defined tensor product on A mod? Like,
No, sorry, that's the thing you want to define.
okay.
Sorry, that's the goal. This is over vect. There's certainly a well-defined tensor product over vect, and it may or may not be the same as that. And it often needs to be corrected, and then you need to figure out what to do, what sort of tensor product to put on A mod to actually make it match this. Sorry, that I didn't phrase that well. Sorry, that was very vague. The nicest case is that you actually do have an isomorphism. But more so, you have an isomorphism preserving associators. And again, this is over. In vect, associators are trivial, so what I really mean by preserving associators is trivializing associators. And at this category level, isomorphisms are not just equalities. They come from maps. And so if you want to say that you have an isomorphism, that means that there are natural maps, or in other words, a natural transformation. So they're maps natural in all pairs, L and L prime. Write it this way. Actually, I'll just modify that equation. So there's a map this way that's often called J, and there's a map this way called J dual or adjoint. Such that they're inverses of each other. If you have that sort of situation, in particular, you're going to send the unit to the unit. And then you can define a coproduct on A the following way. So for a natural transformation from F to F, we want to produce a natural transformation from F tensor F to F tensor F. And we've got this J that helps us do it. Conjugate by J. So now this is like, and now you need to be really careful with like swapping orders of limits, and I'm not being careful. I'm giving you this schematically to give you an idea of how things work, and you can look up in EGNO how this is going to happen in nice abelian categories, or Lurie or Gates-Gorey for how this is going to happen in DG categories. But this thing, roughly, is the limit that I'm being very hand-wavy about swapping is putting the tensor product on the outside rather than the inside. So end of f tensor f may not actually be end of f tensor end of f, but anyway, close enough. And then to make A into a bialgebra, we want a co-unit, and just define that as evaluation on f of 1. So it's sort of the component of that natural transformation on 1, in other words. 1, that's an endomorphism of f of 1. Great. So that gets translated into pictures and into physics and into TQFT. So I only have, unfortunately, time, I think, to talk about the nicest case. But I'll also mention that, there are vast generalizations that are all very useful and show up all over the place. You don't need to always assume that there are isomorphisms in both directions. One of the very common things that arises is that going from f tensor f to f and back might just be a projection. So that map is called J dual J. And this lands you in the world of weak Hopf algebras. Or weak bialgebras, I haven't talked about. I'm not going to talk about that. Or if you don't preserve associators, you get quasi things. You need to add associators in your algebra A to make up for that. Okay, so let me now draw pictures. And there are many beautiful examples in 2 dimensions involving interface categories in 2D that are monoidal. But given time, I'm going to jump to the slightly more interesting thing, which is lines in a 3D. Logical QFT. Expectations. If you want to work in a situation where there might be a topological boundary condition, gives these things names. So here we have our bulk theory T. And there might be a topological boundary condition B. And then there are 2 categories around. There's lines in the bulk, we call CT, and there's lines on the boundary, CB. CB is monoidal. It has a tensor product from collision along the boundary. CT is monoidal and braided and generally ribbon. The ribbon twists might be trivial, but there's from a physics QFT perspective, you're defining if you start with a QFT and say it behaves topologically, there's framing of line operators that needs to be added in that makes this thing ribbon. Or your perspective might be in the world of extended TQFT in 3 dimensions with certain framing data. And that, again, makes this thing ribbon. I'm quite intentionally not calling this TQFT because I don't want you to think I have a particular model of extended TQFT in mind, though I could, and this applies. And much of what I'll say is based on things that Wenjun Yu and I wrote down in a paper from December, where we actually are more precise about models for TQFT. I'm making that comment because, like, if you're given a quantum field theory with an action in a bunch of fields and some inkling that it behaves topologically, you may have no clue what the underlying higher category governing the extended TQFT is. But you can probe boundary conditions and compute stuff. Okay. Aside done. There is more structure coming from interactions between the bulk and the boundary that is sometimes called a central structure on CB. There's a thing called the bulk boundary map. That sends colors, that sends call that beta B. It sends bulk lines to the boundary, collides them with the boundary. That makes CB a module category for bulk lines, because you can collide and then collide. So like collide a bulk line with the boundary and then collide with a boundary line using the boundary tensor product to get your module action. But in fact, there are 2 such things. If I have some sort of fixed, or rather, there's sort of 2. If there are 2 module actions. If I have a fixed boundary line, I can use a bulk boundary map to the left of it, or I can use a bulk boundary line to the right of it. And there's clearly a homotopy between the 2. And the homotopy between the 2 is a half braiding, and so this thing refines to a map to the Drinfeld center. And that's what I mean by a central structure. And one way, if you are happier with module categories than with pictures, one way to say what I mean by a boundary condition for a 3D QFT is through this map. So CB being a boundary condition, as opposed to an interface to some more interesting theory on the other side, means that this thing is surjective. And B, a generator for whatever the two category of boundary conditions is here, implies that this is an isomorphism. And if the theory doesn't have anything other than line operators around, then that would be if and only if, but sometimes there's more stuff. So that's very general. Now I want to try to translate this nicest case of Tannakian reconstruction to pictures. And it requires more. So for the nicest case of reconstruction, which will give me A as a bialgebra. And I keep wanting to say hop, and I might accidentally. And it's hop if there are enough duals around. You actually need more.
Yeah, is that something like CP ribbon?
Sorry?
Enough duals? Should I be thinking like CP ribbon or something? Or sorry, CP rigid? Like the compact projective.
I don't think I know the definition. Sorry, I don't know the CP.
You just look at the compact projectives; they have duals.
Oh, yes. But you also need the category to be generated by them, and that's what I mean by enough. Sorry. Yes, absolutely. So, yeah, like you define an antipode the same sort of way, but in general, Lucas will.
I was saying that also non-projective modules over half algebras have duals. So you probably want them to have duals as well.
Yeah, so sorry, I'll just make a quick comment. So you define an antipode the same sort of way. You use isomorphisms that tell you how duals are actually preserved to define an antipode on the algebra of natural transformations. Typically, so if you're in a very small abelian category, everything might have a dual. If you're in a very large category, it's unlikely that everything will have a dual. There are objects that are like infinite limits, and then you play a game where you assume your category is generated in some nice way by objects that do have duals, define the antipode on that small set, and then take limits to define it on everything. Cool. So to reconstruct as a bialgebra, we actually need two transverse boundaries. And transversality in this dimension looks like this. It means there's an isomorphism between D and N and a bulk theory in the middle and trivial. But the isomorphism needs to be spelled out. So there's some interface between D and N and the trivial interface between the trivial 3D QFT and itself. And for reasons, I do actually remember. I ended up calling this thing K. And yeah, at a technical level, dualizability properties of this interface make your reconstruction game either nice or hellishly difficult. But I am going to gloss over that for now. Great. So this K thing, if I read the picture going up, it's an isomorphism from D collided with N to trivial. Being an isomorphism means I can also read the picture down, and I'll get the inverse. And there are more like coherences that tell me exactly how that thing is the inverse. One consequence is that the category of lines on K is trivial. And great. So now there are 3 or maybe 4 categories around. I've got lines in the bulk. I've got lines on one of the boundaries. I've got lines on the other boundary. And I've got lines on K, or maybe lines on the other side, the trivial theory, which is vect. One incredibly quick way to define fiber functors that I don't love, but is useful for some abstract purposes, is to flip D around and use the bulk boundary map. Start with a line out in the bulk. Actually, let me maybe factor that through collisions. So first, I can start with a line on D and collide it. Sorry, that's some sort of D dual, and collide it with K. Or I can start with a line on N and collide it with K. But when I do that, I get an action on vect. Everything trivializes on K. And so there are maps from something like CB tensor op to vect, and Cn to vect. And these are very schematically going to be fiber functors for the boundary categories. And when there's a bulk boundary map, in fact, there are 2 of them. From the bulk category, I lost it, to either side. And there's an isomorphism between the two. And the composition in either direction ends up defining a fiber functor for, for the bulk category. So one could simply use that picture to do everything, and forget about higher TQFT and and QFT and so on. That sort of thing appears already, or a version of it in EGNO. If with some completeness condition around having actions of Cn and Cd on vect that centralize each other, on one hand looks like Koszul duality. It's sort of a category, a monoidal category version of Koszul duality, but it has names, and so if these actions are faithful, which is a completeness condition, CD and Cn are called dual categories. So this is just like having two algebras acting on C, but now at the category level, and a beautiful thing that happens when you promote to the category level is that you don't actually need bosons and fermions around or DG things around. There's a version of this that makes perfect sense in the abelian setting. Okay. There are better pictures, maybe better for me pictures, possibly not better for you. So other pictures of the fiber functors. So if I want to take a line on D and turn it into a vector space, I can do that by capping off with n. That's L, and I cap off, and I look at the space of states on that thing. And now that's very similar to what I did in 2 dimensions in terms of making sandwiches. And if you compactify to 2 dimensions, say by folding around the line, this looks exactly like a 2-dimensional strip. You can take any of these pictures and turn them into the previous lecture. And on these interfaces goes the transversality thing. And there's an Fn that looks the same. It caps off. Caps a line on N. And with sort of a half circle of D. And now there's the obvious thing you can do in the bulk. You take a line sitting in 3D space and cap it off on both sides. So throw it into a solid cylinder. And 2 transversality seams with N on one side and D on the other. And everything is solid in there. And measure state spaces. transversality shows up immediately in making sure that the tensor identity goes to the identity. If you apply these things to the unit object, you just get empty cylinders, and D and N are transverse, and so you get a one-dimensional state space. And you absolutely need to have that to have any hope of this being an isomorphism. The endomorphism algebras of the respective fiber functors they come directly from lifting the pictures from 2 dimensions to 3D. And the same words that I used before. So if I cap off a line on D, natural transformations of this functor are operators with fixed time extent that live anywhere except the line that I've touched, the line that I've capped off. So I'm not allowed to touch that line. And any such operator can be like moved away topologically onto the end boundary and is going to be supported on some big arc on the end boundary. It might be a point, but it might also just be a big arc. Endomorphisms of this fiber functor are any operators supported on a big arc on the D boundary, and endomorphisms of the bottom thing are supported on a big arc on N or a big arc on D. And because of transversality, they separate. And these all end up being bialgebras, or in nice cases, Hopf. So this I'll call Hn. It's the thing that acts here. Hd is the thing that acts here. And here, at least as a vector space, we get the tensor product happening.
I have some trivial housekeeping questions. So Hn is endomorphisms, it's natural transformations of Fd. And you're saying that these all look like adding extra operators on this arc. Thank you.
Yeah, exactly. They're like morphisms from the bottom to the top. Like it's like you've got Fd on the bottom, Fd of L on the bottom, and Fd of L on the top. And you want it to be natural with respect to L.
Okay. Not on the top and bottom, but like on the top and bottom half of the full convention picture?
Yeah.
Okay.
So I'm sort of going up, and so I want a morphism between F of L and F of L. That's natural in L. And so it can't touch, you need to carve out a little neighborhood around L and be trivial at the bottom and trivial at the top. And topologically, that like the complements of L and the bottom and the top can be contracted onto the green line.
And the contraction thing is this surjectivity that you need, or?
No. That's just I'm just using topological invariance to, yeah.
Right, and as long as I'm asking a ton of questions, how much would fall apart if I wanted to say rep qt instead of vect as my other theory?
Very little. The whole thing can be rephrased with something else on the other side. And there's a relative notion of transversality, which is this picture with t prime. Maybe it's like rep qt.
And then does it still need to be the identity between T prime and T prime? Or could that be some other?
If it's the identity between T prime and T prime, you have options. So if you put something else on the other side, these won't be bialgebras or Hopf algebras. They will be Hopf algebra objects in the thing on the other side. Let me just say that and actually draw them. So there's a useful state operator correspondence here. So I've given you operators on this green line, and maybe that's hard for you to think about. There's a state operator correspondence which says operators supported on any sort of submanifold should be states on the link. So the quantization of the field theory on the link of whatever that submanifold is. So we thicken the green line a little bit and take a neighborhood of the thickening. Or sorry, take the boundary of the thickening. So Hn as a vector space also looks like states on, is going to be the boundary of the thickening of the green line. All right, and now you need to stretch your imagination a bit to figure out what that is. And it ends up looking like a rectangle with most of that rectangle is sitting inside the bulk theory. And it has two little boundaries on D. And it has two long boundaries on N. It's sort of infinite extent in time, and just sort of drawing the thing as extended in time, but if you were applying the TQFT functor, you would just say it's like states on that rectangle. And this is a thing that in a I think in a semi-simple context, David Reuter talked about 5 or 6 years ago as being a Hopf algebra. So if I want to, now your generalization to having something else on the other side is really nice. This is sitting in a trivial theory. And so I'm just saying it states on this because it's some big line operator in a trivial theory, and a big line operator in a trivial theory is a vector space. If it's not in a trivial theory, you get a big line operator in some other braided tensor category. And so this will define a Hopf algebra object in some other category. Similarly, HD has a description as a state space on a similar thing where you stare at it, the N's and the D's are just swapped around, and there's some reversal of orientation. So it actually looks nearly the same. And the endomorphisms of the bulk fiber functor end up looking like states on an annulus. With 2 D boundaries and 2 N boundaries. This times. And you can use transversality to cut the annulus into 2 rectangles, which is where this comes from. I've also sort of, just say that. Okay. I keep saying these are bialgebras, or in nice cases, Hopf algebras, and I haven't told you why. And so I want to tell you why. So I want to keep that board. J, that J, the natural transformation between tensoring before and after the fiber functor. Let's do it for, say, Fn. It really doesn't matter. J looks like this. It takes the functor applied to two line operators on n, and gives me a morphism to the functor applied to a single line operator on n. And there's a natural way to do that with a pair of pants, where there's sort of a d in the front and an n in the back. And the whole thing is filled in. And we're going from bottom to top. So that's F tensor F, and this is F, oh, sorry. No, this was 2 lines. So there's L, there's L prime, and this is F of L tensor L prime. And if you know what J is, you can just apply formulas to figure out the pictures for everything else. So what's the coproduct of a sorry, I had a name for these things. I think there are other names around in the literature, but to me they look like little electric sparks moving up and down a pair of wires. And so we ended up calling these spark algebras, and I've been trying not to use the name, but I'm just going to use it. So these are sparks. And the coproduct on a spark on n, on D, sitting on the outside, is going to be defined by a double pair of pants. I'm just going to draw it sort of schematically, but it's a thing that looks like this with D on the outside, and you insert there's A inserted in the middle, and so that's J, that's J dual, and it now gives you a natural transformation from F tensor F to F tensor F. But you can also just read that as, well, you can try to decompose this picture any way you want. So in particular, if you can figure out what this operator stretched all the way across looks like when you bring it to the top, and maybe it decomposes into some things over here and some things over here, that's a computation of the coproduct. Great. Transversality ensures a bunch of things. Sorry, I should also tell you what the co-unit is. That's easy. That's insertion into a solid sphere with something like that. This is for HD, but I can put a thing on the other side as well. And transversality ensures, through nice manipulations, that the coproduct is actually an algebra morphism, and that the co-unit obeys the thing it's supposed to with respect to the coproduct, and that's how all that fits in. And I'll say the last fun part of this. So sorry, this is maybe too many details, but also just a really nice setup. There's a pairing between HD and HN, and it's non-degenerate just because these rectangle state spaces are the same state spaces up to a reversal of orientation. HD and HN are dual, but they're actual dual as bialgebras. You can spell that out in topology to your heart's desire, and it's quite fun. The fun thing to figure out is what the non-degenerate pairing actually is between them. It takes a spark on D and a spark on N and sends it to an insertion in the 3-ball where the two are linked. That's a direct topological derivation if you have time to think about it. Then the last bit is figuring out that there's an R matrix on the double that actually does the right thing with respect to braiding. There's an R matrix and there's a ribbon element in the bulk category. And again, using gluing along rectangles and some topological operations, that just ends up being the inverse of the Hopf pairing. And if things are infinite dimensional, that needs to be interpreted in a distributional sense. So it's basically H inverse. And that altogether turns into a theorem that that uses the Dirichlet double. That works equally well in a DG setting as it does in an abelian one. Okay, so that's the simplest case. I am glad I did not start with other fiber functors and the more complicated cases. I'll give you, I'll maybe give you one or two examples quickly and stop. If you consider finite gauge theory, with trivial cocycle, then both N and D exist. They're transverse and complete. And that's in contrast to 2 dimensions. D is Dirichlet and N is Neumann. And there's then a direct computation of the sparks. So what's HD? We have a Dirichlet boundary condition with transversality interfaces to Neumann on either side. and we're trying to ask what's the algebra of defects stretching across from one end to the other, D has global symmetry. And so these things are labeled by global symmetry transformations. And that produces the group algebra. Hn is a strip of n. So fluctuating gauge bundles in the middle, trivialized on either side. And this has Wilson lines stretched across in various representations that are framed at the two ends. And so we end up with matrix elements of all the different Wilson lines. And matrix elements in all the representations give us the algebra of functions on G. And they both end up having the bialgebra, in fact, Hopf algebra structures you want, and they pair together into a Dirichlet double. And then the thing I had actually wanted to figure out was twists of 3D n equals 4 theories, which include compact gauge theory, whose complexification I'll just call G. And it ends up looking identical to this, except everything's in the DG world and very infinite. It's in the DG world, but the algebras still end up being in degree 0. HD ends up being distributions on G, which is the thing that is the correct substitute for the group algebra in the infinite case. And Hn is still functions on G. And functions and distributions are dual to each other as topological vector spaces. And that's also a famous, this is not new mathematically, this is a famous Drinfeld double construction. The thing that was nice was to actually pin down the structure of a braided tensor category in the physical QFT and to make sure there were no other quantum corrections lying around and so on. And we can throw in matter and other stuff. All right, I'll end by saying, like, this was a specific construction that I told you about in the last half hour. But the method is extremely general. You can mess with lots of other fiber functors and ask faithful/completeness questions and ask questions about tensor products. In particular, how pairs of pants behave and how, like, you know, whether the coproduct is an algebra morphism or not, and what you need for it in pictures. And it's quite fun to do that. But yeah, I encourage you all to explore on your own and relate with things like weak Hopf algebras and tube algebras and all of that fun stuff. Okay, thanks.